There's a huge misconception with Newton's third law, because often people quote it like they do in the movies. So you've probably heard it before, for every action there's an equal and opposite reaction. That's not how I actually like to think of Newton's third law, because it leads to a lot of misconceptions, like the one that we're going to talk about here. So I've got a box, and it's at rest on the ground. Let's draw the forces that are acting upon it. So hopefully you recognise we've got the force due to gravity. It acts from the centre of mass of the object and points downwards. Let's maybe put mg. We've also got another force acting, and that is the normal force. And that's because this object is in contact with a surface, so that means it's going to be experiencing a normal force. That's the definition. In VCE Physics, if we're doing a formal drawn question, we need to show it from the point of application. So that normal force is due to the contact with the surface, so we need to draw it here. Now, you probably recognise, I'm trying to do it by eye, but these forces need to be the same length. I'm going to call that F subscript n for the normal force. And then you might quote to me, well, these two forces are equal in magnitude, but opposite in direction, so therefore they're a Newton's third law pair. That's not the case, and that's a big misconception. Newton's third law pairs mean something very particular. I think this is a better way of actually quoting and talking about Newton's third law. So it says, whenever an object applies a force to a second object, the second object applies an equal and opposite force to the first object. It's not as catchy as the other one, but I think it is a much more useful representation. It hones in on something that the equal and opposite reaction doesn't hone in on. It's talking about two objects exerting forces on one another. And we can come up with lots of examples for this, but let's look back at this box example for a moment. So what's the issue then? Why do the two forces that I've drawn here not represent a Newton's third law pair? As we've mentioned, they're equal in magnitude and in opposite directions, but there's a fundamental thing that's missing. These two forces are acting on a single object. When we're talking about a Newton's third law pair of forces, they're two forces as the result of two objects exerting forces on one another. This is the force due to gravity on the box, and the normal force also acting on the box. So, big red flag there, because we've got two forces acting on a single object, they are not a Newton's third law pair. Let's see if we can actually come up with which force would pair with each of these forces in a Newton's third law pair situation. Well, I find it useful to rewrite this. And in fact, let's talk generally before we actually get into this example. This is rather wordy. What you might like to write this as instead, we would write the force on A by B. So they specifically like to have it in that order. On A by B. That is equal to negative F, because we said the forces were in opposite directions. So negative force on B by A. So again, we've got that on an object by another object. You will always know if you've got a Newton's third law pair if you check that you've got this sort of scenario going on. So let's go back to the box. So it's a little hard possibly to visualize what two objects are being acted upon, are doing the interaction, I should say, with these forces in the way that they're currently written. I've got Fn and I've got mg. So let's write what mg is using that sort of template that we had before. Mg is actually the force on box by the earth. So, if I was interested in the Newton's third law pair with this, I would need to reverse the direction, I would need to reverse the order of these words. So that means that the Newton's third law pair to the force due to gravity on this box, F on box by earth, is the force on earth by the box. So rather stylistically, I have imagined the earth here. And clearly the spot that I've drawn at the bottom here is not the center of the earth. But if I were to draw this to scale, it wouldn't work anymore. That Newton's third law pair, we draw it acting on the center of mass of an object. So pretend this is the center of the earth. So it would be equal size F on earth by box. box. The box exerts a gravitational force on the Earth, as strongly as the Earth exerts a gravitational force on the box. The result of those forces are very different though, because of the different masses of the objects. Here's the first Newton's third law pair. We've got force on box by Earth, force on Earth by box. Let's now apply that same logic to Fn. What actually is that? That's force, again, on the box by floor, we'll say. So this is another way that we can be alerted to the fact that this is not a Newton's third law pair, Fn and mg. This is force on box by floor, whereas this is force on box by Earth. We don't have those two objects swapping those words around. So, what is the reaction to this? What is the Newton's third law pair? Well, that's the force on the floor by the box. So here's that reaction force, force on floor by box. I've had some students in the past going, wait a second, isn't force on floor by box just the same as mg? In this instance, yes it is, but in other instances, if you had a car going over a speed bump or going under a dip, that normal force actually changes. So it's not always the same. So it would be incorrect to say that they're always the same. So how do we know that this is a Newton's third law pair? Force on box by floor, and then force on floor by box. We're talking about two objects exerting forces upon one another. Now I might have people wondering, why don't we have negative signs in there? The direction of the arrow is telling us about the direction of these forces, so we don't need a positive or negative because the arrow is doing that work for us. So I hope this has helped you understand what Newton's third law is in reference to. Let's do a couple more examples in case you're not sure, but if you feel confident, you could just stop the video now. One important application, I need to be clear, this is not drawn to scale in any way, is forces on objects that are orbiting each other. So the Earth and the Moon, for example, force on Earth by the Moon is equal to the force on the Moon by the Earth. Now you might say, hey, wait a second, the Moon orbits the Earth. Sure. The reason the Moon experiences a different effect of the force is because it has a very different mass. And I'll link a video that I really recommend that you watch that talks about that there. Let's look at another example. So I've drawn a highly accurate diagram here. We've got a foot kicking a ball. Force on the ball by the foot is equal in size but opposite in magnitude and indeed a Newton's third law pair with the force on the foot by the ball. We've got two objects exerting forces upon one another. The effect of that force, the acceleration of the objects, is very different due to the different masses. So remember team, don't be fooled into saying the normal force is a Newton's third law pair with the force due to gravity here. You need to follow that formula that we spoke about before. Force on A by B is equal in size, force on B by A, but opposite direction, which we represented with a negative sign when we wrote it out as an equation, but when we have arrows, we don't need to put negatives there. And I've put for this particular example, what we would actually talk about the Newton's third law pairs with these two forces being. If you ever find yourself in a situation where you think Newton's third law pair of forces is cancelling out, watch out. You've got two forces acting on one object here, or you're incorrectly thinking these forces cancel. The forces we spoke about before, force between the Earth and the Moon, certainly doesn't cancel, otherwise the Moon would have floated off into the universe. Force of the foot on the ball and the force of the ball on the foot cannot cancel. They're two separate forces acting on two different objects. I hope this has been helpful. Let me know if you have any questions, and good luck.